Welcome everyone to lesson 3.3 of Precalculus, which is all about sine and cosine function values, or what I'm going to affectionately refer to it as the creation of the unit circle. So let's get started. The first major thing to note is we're going to bring back special right triangles. Hopefully your geometry teacher talked about this in geometry. I know that I do. And they are special triangles based off of angles that have really specific ratios for their side lengths. The first one is the 45-45-90 triangle. And if you had a discovery-based approach to mathematics, you would have discovered that this is the diagonal of a square. So if we have the diagonal of a square, those side lengths are 1, the length of its diagonal is the square root of 2. And you can do that with Pythagorean theorem, right? So 45 degrees, 90 degrees. Radians, that would be pi over 4, and pi over 2, all adding together to be a whole pi, which I think is really, really cool. So that's all fine and dandy. For dealing with the unit circle, for trying to build the unit circle from scratch, we want the diagonal, we want the hypotenuse to be 1, so that the radius of the circle is 1. So wonderful things with triangles is we can scale them down by using a common scale factor. So if I look at these two triangles here, if I use a scale factor of 1 over the square root of 2, which again, like we don't technically like, but it would turn that square root of 2 into a 1. It turns the 1 into 1 over the square root of 2, which is improper. Making it proper turns it into the square root of 2 over 2. So for pi over 4, or 45 degrees, sine and cosine are both square root of 2 over 2. Quite nice. So if we take these dilated triangles and map them onto our circle, we can actually find values for every increment of pi over 4. So again, if we drop down a triangle here, this triangle is 1 for 1 for this triangle up here, which makes the point the square root of 2 over 2. Square root of 2 over 2. So that's great. What would it be over here? So even before we fill in the angles, let's fill in the rest of the circle. Well, I know that that's a mirror reflection. A circle has wonderful symmetry. This would be a reflection, and the x-coordinate would be negative. So negative root 2 over 2, comma, root 2 over 2, just because it's a reflection. This point down here, also a reflection, but this time the y is going to become negative. So negative square root of 2 over 2, comma, negative square root of 2 over 2. Quite nice. One last reflection. This time the x comes back to be positive, so we get the square root of 2 over 2, comma, negative square root of 2 over 2. So that's great. We got 4 angles from one special triangle. What are the other points here for? Well, they're the quadrant angles. If we notice, all of them aren't really made from triangles anymore. They're made from line segments. And we know that because we're dealing with a circle, the line segment's length has to be 1. So using that and what I know about our coordinate system, I know that this would have to be an x-coordinate of 0 and a y-coordinate of 1. The reflection of this angle here would be negative 1, 0. And a reflection of the angle at the top would be a 0, negative 1. Great. Last but not least is the angles, and we're going to do increments of pi over 4. So we're going to start at 0, pi over 4. Well, 2 pi over 4s is 2 quarters makes a half. Half and a quarter make 3 quarters. 3 quarters and a quarter make a whole. A whole and a quarter make 5 quarters. 5 quarters with a quarter make 6 quarters, or 3 halves. 3 halves and a quarter make 7 quarters. And then 7 quarters and a quarter make 2 wholes. So that's the way I like to think about it anyway. So that gets us back there, and we can infinitely repeat that pattern. Now, I'm going to say this now. It really, really is imperative for you. It is so important to try to have a way of having these down. Trying to make sure that you, one, yes, understand where they came from, what they are, why they work. But it's super important to be able to go from memory and pull some of these values out. And the reason why is they come up all the time. These special values of sine, cosine, we'll get to tangent, and then the really cool ones of secant, cosecant, and cotangent. You have to be able to pull some of these values from memory or have a way to devise them without having to rely on essentially a crutch of the unit circle. Unit circle is great. It's beautiful. It's marvelous. But so many, and I've seen it so many times, students are reliant on it. Yes, I know how to use the unit circle, so I'm okay, until I don't have the unit circle and I don't know what I'm doing anymore. We have to be able to do this without. So we're going to challenge ourselves. We have these questions here, and I purposely removed the unit circle from the screen. How can we find what these values are? So I want you to start to think in terms of whatever works for you. I personally think of triangles. The unit circle we created so far, based off of 45, 45, 90 triangles. So let's draw those triangles in the way that would look, right? So for sine of pi over 4 quadrant 1, the triangle itself would look like this. Pi over 4. And I know that for a 45, 45, 90 triangle, it's 1, 1, square root of 2. I know that we simplified them before. But we can just use our right triangle trig from this. Sine is opposite over hypotenuse, 1 over the square root of 2, which we know would then become the square root of 2 over 2. And I didn't have to look at a unit circle. I didn't have to use some sort of crutch. If I have these right triangles memorized, it makes life infinitely easier. The only one that doesn't really count for that is your quadrant angles. Sine of pi. That means we're going directly left. That point is -1, 0. And I know coordinate-wise, sine is the y. So this is 0. -3/4. Well, if I think about my circle again, I'm starting here, 1/4, 2/4, 3/4. So I'm in quadrant 3. So I'm going to draw my triangle like I'm in quadrant 3. Reference angle would be pi over 4. And that would be 1, 1, square root of 2. But we went left, so it's negative, and we went down, so it's negative. So same idea here is sine is opposite over hypotenuse, so this would be -1 over root 2, which simplifies to -√2 over 2. So again, not relying on the unit circle. It's great, and it makes connections to so many different things possible, but we're not using it as a crutch, we're using it as a tool. 3 pi over 4, well, I know that 3 pi over 4 is in quadrant 2, so my triangle is going to look like this. Pi over 4 is our reference angle. So we are going left 1, up 1, hypotenuse of root 2. So cosine is adjacent over hypotenuse, so that would be -1 over root 2, which becomes -√2 over 2. Perfect. 7 pi over 4 is in quadrant 4. So I'm going to draw my triangle as if it's in quadrant 4. Pi over 4 is our reference angle. And we have 1, 1, square root of 2. We are going right, so that's positive, and we are going down, so that's negative. But we went adjacent over hypotenuse. That is 1 over root 2, which is root 2 over 2. Perfect. Negative pi over 7 pi over 4. That would be in quadrant 1. Pi over 4. 1, 1, square root of 2. I think we can guess what this is. It's going to be square root of 2 over 2. So that's how I do it. I rely on the triangles. And I've had those memorized for a while. And you may have also had these memorized for a while. They might be back in there. We might have to dust them off and get the cobwebs off. But hopefully they're in there and they're ingrained. Everything can be used with the triangles except for your quadrant angles. So halves of pi or whole pies. We can also see something cool. All of the angles that had a denominator of 4, their answer for sine and cosine was positive or negative square root of 2 over 2. And that's also something you could memorize. That is a connection you can make. So what other special right triangle do we have? We have the 30, 60, 90 triangle, which converted to radians would be pi over 6, pi over 3, and pi over 2. And the ratios of their sides are 1 to square root of 3. So if we scale those down, so again, we want the hypotenuse to be 1, we would use a scale factor of 1/2. So we get triangles that are 1/2, 1, and root 3 over 2. And if I use my right triangle trig, I then get the sine of pi over 6 is 1/2, the cosine of pi over 6 is root 3 over 2, and then they switch for pi over 3. So sine is root 3 over 2, and cosine is 1/2. Quite nice, not bad. Again, we can increment these now on our unit circle. so that we have all of the increments of pi over 6 or 30 degrees. So, and I want you to think about it, right? If I again look at this as a triangle and I'm dropping this down, this leg is obviously shorter than this one. So its height is smaller. Its height is going to be 1/2, and its width is going to be the square root of 3 over 2. Where this one is the exact opposite. Its height is higher, and its width is smaller. So its width is going to be 1/2, and its height is going to be the square root of 3 over 2. Then we can do exactly what we did before, and that is reflections. We can reflect these points. So I again see 1/2 and the square root of 3 over 2. Problem is that we're negative x's, so my 1/2 is negative. And this point here would be a reflection of this point. Again, negative x's. Great. Then we go to quadrant 3, reflection of both. The y's now become negative. So negative root 3 over 2, negative 1/2, and this would be negative 1/2, negative root 3 over 2. And then finally one more reflection where the x's become positive. So we have positive 1/2, negative root 3 over 2, and then root 3 over 2, and then negative 1/2. So not bad at all, really. Just takes some practice and getting used to. Now, here's where you got to think about it a little bit, and we'll notice some patterns here. So pi over 6 plus pi over 6 is pi over 3. This is 3/6, which is 1/2. 4/6 also reduces to 2/3. 5/6 doesn't reduce. 6/6 reduces. 7/6 does not reduce. 8/6 reduces. 9/6 reduces. 10/6 reduces. 11/6 does not reduce. And then 12/6 does reduce again. Look at where the angles are and look at their denominators, right? The denominator of 6, which all have the same corresponding patterns, just negative and positive versions, are the ones closest to the x-axis, where the denominator of 3's, which again have a certain pattern, all the ones closest to the y-axis. So the symmetry and the beauty of this really does come into play. All of the denominator 4's have the same behavior or the same values, just positive and negative. Same thing with denominator 6, denominator 3. So I think that's really cool. So again, let's find some values, but let's not rely on the circle. We don't want to use the circle as a crutch. We want to use it as a tool. So I personally draw the triangles. But again, if you have your method or you've learned a method, use that if you enjoy it, right? So pi over 6 down. So pi over 6 down would be in quadrant 4. So I'm going to draw a quadrant 4 triangle. Now, pi over 6 is our reference angle. Pi over 6 is the smallest one. So across from it would be the smallest side, which means that this is the rest of the information, right? We're going down though, so then 1 is negative. Sine, opposite over hypotenuse, would be negative 1/2. Again, not too bad. You just really have to get used to it. 2 pi over 3 is 1/3 away from being whole. So that's in quadrant 2. And this one is a little bit larger. So 1, root 3, 2. We're going left, so it's negative 1. And sine is opposite over hypotenuse, so the square root of 3 over 2. If you realize, we don't have to rationalize these, which is also quite nice. Sine of 4 pi over 3 is 1/3 larger than a whole pi. So we're in quadrant 3 now. And mine might not be to scale, but pi over 3 is the larger of the two angles. So this is 1, this is root 3, this is 2. And we went left, so it's negative. We went down, so it's negative. Sine would be root 3 over 2, negative. Not bad. Cosine of pi over 3, well, that one, quite simple. Pi over 3. Larger side gets the larger angle gets the larger side. Smaller angle gets the smaller side. Hypotenuse is 2. And we went right and up, so both of them are positive. Cosine adjacent over hypotenuse, this would be 1/2. Cosine of 5 pi over 6, that's 1 less than a whole pi, so we're in quadrant 2. Pi over 6 would be a reference angle, Smaller angle gets a smaller side. Root 3, 2. We went left, so this is negative. So our answer here would be negative root 3 over 2. And negative pi over 2. That's a quadrant angle. That's going down, which means the point is 0, negative 1. Cosine is the x, so this is 0. Not bad. Again, don't use the unit circle as a crutch. Use it as a tool, right? Think of the symmetries. Think of what the triangle would look like, and then draw the triangle. That is the Mr. Whaley certified way of doing things. And I know that's helped quite a few of my students in the past. But again, everybody has their preferred preference. Whatever way encodes it the best in your brain is the way that you got to go. Some people have the whole circle memorized. I had a student, we referred to him as the unit circle expert, and he had the whole thing literally memorized. We called him one day when he was sick and was like, what point corresponds to like 7 pi over 6? And he was able to spit it out, even being sick and absent, which I thought was really, really cool. But again, you don't have to memorize the circle. That's just something that he really, really wanted to do, and he did it, and he was successful. Here is the circle put together. So if we put the quarters together with the sixths and thirds together, we get this really nice circle, and we can see the symmetries laid out here. And again, because it's a unit circle, the x-coordinate corresponds to the cosine of that angle, and the y-coordinate corresponds to the sine of that angle. If you want the tangent, you just do the y divided by the x, right? Now, here's a trick for you, because tangent, sometimes you get fractions over fractions. For example, if I want the tangent of 3 pi over 4, and we haven't gotten to tangent, but I really want to make sure that you're okay. If I want the tangent of 3 pi over 4, that would be equal to root 2 over 2 divided by negative root 2 over 2. That looks like a nightmare, right? What you can do is, if you notice, all of the angles that aren't quadrant angles have a division by 2 as part of their coordinates. Erase them. Make your life easy. Instead of doing this, instead have root 2 over negative root 2. Oh, that's easy. That's negative 1. So, just a trick for tangent, but again, we'll dive into that later. So, again, you must have this memorized in some capacity. I don't have the circle memorized as a circle. I've memorized it as 2 special right triangles in 12 different ways with 4 quadrant angles. And if that works, awesome. If you have some other way, use that. Here's a way that works for some people, and that is, there is a pattern here. If we go by the first quadrant angle of 0, right, I know that the x-coordinate is 1, and I know the y-coordinate is 0. I can also rewrite that as the square root of 4 divided by 2, comma, the square root of 0 divided by 2. And you might see where I'm coming from this. If I increment the cosine and the sine by 1 each time, I'll get all of the values. So first one, the 4 goes down to a 3, the 0 goes up to a 1, square root of 1 is 1, so you get 1/2. Then you increment again, 2, 2, 1, 3, and then 0, 4, which is really cool. And again, simplifies to all of the coordinates. Very nice pattern. And you can complete it by doing the symmetry, right? Now, instead of the x's going down, the x's are going up, and the y's are going down, all incrementing by 1. So we have 1, 3, 2, 2, 3, 1, 4, 0. And again, you can repeat that pattern to get the rest of them. I think that's a really cool pattern, and if that works, if that's the way you remember it, awesome. It doesn't work for me. It just didn't jive. It just didn't encode properly for me in that way. So this is why I'm showing you more than one way to do it. So unit circle, great. We built the unit circle. It's beautiful. It's fabulous. What if we're not dealing with the unit circle? What if we're dealing with a circle that doesn't have a radius of 1? Well, we've kind of already established that sine was y over r and cosine was x over r, which means the coordinate points, instead of being cosine sine, is r cosine, r sine. And this is going to play into polar coordinates way at the end of the unit, which, again, I think is really, really cool that we're making these connections earlier on of I can take an angle and I can take a radius, and I can get an x comma y. And so this part of the lesson, we are going to take angles and radiuses and get xy coordinates. And we're also going to take xy coordinates and we're going to get radiuses and angles, which I think is awesome. So again, we're going to build into this at the end of the unit. When you see anything that mentions polar, that's what it means. Instead of dealing with x's and y's, we're dealing with r's and thetas. So if we are given an angle in standard position and the radius of a circle, can we find the xy coordinate of the point? Well, yes. The x coordinate is r cosine, and the y coordinate is r sine. Might help to use theta. So x is equal to 6 cosine of 5 pi over 6. And this is where, maybe I should have memorized this, or I should have taken the time to memorize this, comes into play. Well, what are those values? Well, for me, I'm going to draw the triangle. 5 pi over 6 is 1/6 less than a whole pi, so I'm going to draw a triangle that looks like that. Pi over 6, smallest side gets the smallest angle gets the smallest side, so far and so forth. I went left, so the root 3 is negative, so I know that this cosine here is negative root 3 over 2, negative root 3 over 2 times 6, and the y would be 6 times 1/2. So this would turn into negative 3 root 3, comma 3 as our point, x comma y. Not bad. Again, you got to have your sines and cosines known, but not bad. What about this one? This one looks fancy. We're also dealing with a first quadrant angle. Might help if I write the angle a little bit better. Pi over 3. And I know that for pi over 3, that's the larger side, so it's going to get the larger angle gets the larger side. 1, 2, all of them positive because we're in quadrant 1. So again, we're going to have r cosine, comma r sine for our x comma y. So we're going to have 7 cosine of pi over 3, comma 7 sine pi over 3. Cosine would be 1/2, so this is 7 halves, and sine would be root 3 over 2, so this is 7 root 3 over 2. And those really don't reduce. That's it. We don't have to convert them to decimals or anything like that. Just leave it like that. So that's quite nice. Very, very easy and simple if you remember what sine and cosine are to take an angle and a radius and get xy coordinates. What if I have xy coordinates and I want to find what the radius of a circle would be and the angle in standard position would be to produce those coordinates? Well, this is where we have to think a little bit outside of the box. These are our coordinates. Essentially, we're drawing a triangle with these, right? And you know what? We have a negative x. So I already know that we're in quadrant 2. We have, we have a negative y. We're in quadrant 4, Mr. Whaley. I'm failing already. We're going down root 2 over 2. We're going right root 2 over 2. So our radius, it's a right triangle. R squared is equal to x squared comma y squared. So root 2 over 2 squared plus root 2 over 2 squared. If you square a fraction, you square the numerator and denominator separately. So I have 2 over 4, which is 1/2. So I have 1/2 plus 1/2. R is equal to, so r squared is equal to 1. So r is equal to 1. You're always going to deal with a positive radius here. So if r is 1, this is the unit circle. And you might have already noticed it with the coordinates of the point. This is the unit circle. So we're going to have a denominator of 4 because we're got root 2's, right? And we're 1 less than a whole, so this would be 7 pi over 4. So the radius is 1, and the angle is 7 pi over 4. You always want to give an angle between 0 and 2 pi, just for simplicity's sake. Don't give me something coterminal that's like 5 rotations over. Make it simple. This one here might be a little bit more difficult to see. So again, I'm going to use my knowledge. I know that both are negative, so we're in quadrant 3. I'm going to draw a triangle in quadrant 3. and I know that the x is negative 3 root 3 over 2. The y is negative 3 over 2. I don't know what the radius is, so r squared is equal to negative 3 root 3 over 2 squared plus negative 3 over 2 squared. Well, negative 3 squared, the negatives, they go away. We're squaring, right? 3 squared is 9 times 3 is 27 fourths. 3 squared is 9, so this is 9 fourths. 27 plus 9 is 36 fourths, which is 9. Nice. So that's r squared. So r is equal to 3. If r is equal to 3, and I divide everything by 3, it puts me back on the circle. So if I change my 3 into a 1, this into that, I get a better idea. Now, I notice that my height is 1/2. So my height is shorter than it is long. So it's not as tall as it is wide, which means that it's going to be a denominator of 6 angle. And since it's in quadrant 3, it would be an angle of 7 pi over 6. And we can check this in a little bit if you want to double check that I'm right, which I know I am. Last but not least is this one here. And we're going to do the same idea. I'm going to draw the triangle. Negative x, positive y, we're in quadrant 2. And x is negative 2, y is 2 root 3. So r squared is equal to negative 2 squared plus 2 root 3 squared. Negative 2 squared is 4. 2 root 3 squared. 2 squared is 4 times 3 is 12. So 4 plus 12 is equal to r squared. So r is equal to, that would be 16, so that would be 4. So let's divide everything by 4. Divide everything by 4, we get 1 over 2 over 2. So that is taller than it is wide, which means that it is a root. It's a denominator 3 angle. And the one in quadrant 2 would be 2/3. So we want an angle of 2 pi over 3. And if we want to double check this, again, we had half root 3 and then half root 3. So half and root 3 would be over 3 if the half is in the x, and the half is in the x, and if the half is in the y, it is going to be a denominator 6 angle. So we should be good there. That is it. If you have any questions, please make sure you ask. Otherwise, I'll see you in the next lesson.